This video we're going to do some calculus problems dealing with the fundamental theorem of calculus. Essentially we're going to start evaluating definite integrals, and we're going to stop using Riemann sums, having to get limits as n goes to infinity. If the sum of areas is a bunch of rectangles, that's a bunch of work. Fundamental theorem of calculus is going to make these much simpler. Let's just do some examples here. So the first one, we're going to do an integral from 2 to 4 of x to the fourth plus 5 dx. So what we're going to do here is we're going to first of all find an antiderivative. So we have to find something that will differentiate to x to the fourth. Now the general rule, so this is an indefinite integral. Maybe let's write this in, how about red over here? Indefinite integral, if I have x to the n, I want to find something that differentiates to x to the n. I want to find an antiderivative of x to the n. The general formula is I do x to the n plus 1 over n plus 1, and then you can add any constant you'd like a plus 2. For the sake of doing the definite integrals, we're typically going to choose that constant to be 0. It won't really seem like it matters at all. If you get to, say, differential equations, those kinds of things, this constant will come into play here for certain things. Okay, so what we're going to do here is then x to the fourth, we add 1 to 4, that's 5, so that gives us x to the fifth, over 4 plus 1, that's over 5. So we have x to the fifth over 5. If we took a derivative of that, let's just maybe do that. Derivative with respect to x, x to the fifth, that's 5x to the fourth. Well, let's do a derivative of x to the fifth over 5. 5x to the fourth over 5. The 5's cancel, and you get your x to the fourth. So that will differentiate to x to the fourth. What will differentiate to 5? Well, I can just kind of think about this a little bit and say it's 5x. Or you can actually use this rule over here with noticing that 5 equals 5 times 1, which is x to the 0. And so the antiderivative of 5x should be a 5. I can just pull that out, and then I get x. Sorry, not 5x. The antiderivative of 5 should be 5 times x to the 1 over 1. That is 5x. And I should have my plus c's here as well. Okay, so I find an antiderivative of x to the fourth plus 5. That's x to the fifth over 5 plus 5x. And then I'm going to evaluate that at x equals 2 and x equals 4. So what I'm going to do first of all is plug in the 4. So that's 4 to the fifth over 5 plus 5 times 4. So all I did is put my 4 in for x, and then I'm going to subtract what happens when I put in the 2 for x. So that's 2 to the fifth over 5 plus 5 times 2. And I just get some number here. Let's see, this is going to be 2 to the 10th, which is 1024 over 5 plus 20 minus 32 over 5. 2 to the fifth is 32 minus 10. I'm just going to go to my calculator and simplify that. Probably wouldn't be that bad to do. Probably didn't need to even go this far. Could have gone up to this 4 to the fifth over 5 plus 5 times 4 and so on and put that in. Minus 32 divided by 5 minus 10. Calculator will spit out something. I'm going to change this to a fraction. Typically we like our exact answers better. So it was 1042 over 5. And that's really our answer there. Next one. You're going to integrate from pi over 3 to pi over 2 cosine x dx. So this is a trig function, and I just need to remind myself of my trig derivatives. Derivative with respect to x of cosine of x is actually a negative sine x, and the derivative with respect to x of sine x is a positive cosine x. So when I find an antiderivative of cosine x, I'm going to think about what differentiates to cosine x that's actually positive sine x. So my antiderivative of cosine x is sine x, and then I'm going to evaluate that at really pi over 2, and then subtract that, evaluate at pi over 3. So I get sine of pi over 2 minus sine of pi over 3. See, sine of pi over 2 is 1. Sine of pi over 3 is square root 3 over 2. I could rewrite this maybe as 2 minus square root 3 over 2, although 1 minus square root 3 over 2 is probably just fine here. Next one. Integral from 0 to 5 of secant squared x dx. This one's a little bit, well, tricky, although if you identify this, hopefully you'd be able to do this pretty easily. And I have to think of more trig derivatives here. So this is going to be dealing with either secant x or tangent x here. Turns out that if you differentiate secant x, you get secant x tangent x. It's kind of like what we have there, but the derivative of tangent x is much simpler. It's just secant squared x. And so what that means is my antiderivative of the secant squared x is tangent x. Evaluate from 0 to 5. So this is tangent of 5 minus tangent of 0. Tangent sine over cosine. Sine of 0 is 0. Cosine of 0 is 1. So tangent of 0 is 0. So my answer at the end is just tangent of 5, whatever that works out to be. Next up, integral 0 to 5 e to the 3x dx. This one's trickier here. And so what I have is that if I differentiate e to the x, I'll get e to the x here. So that's basically what we have, but we have that 3x up there. So what I'm going to do is I'm going to think about, well, what if I differentiate e to the 3x? Well, by the chain rule, I'll get e to the 3x, but then I have to multiply by the derivative of 3x, that's 3. I'm going to put that out in front. That gives me 3e to the 3x. So what I could do is I could rewrite this as an integral from 0 to 5, 1/3 times 3e to the 3x dx. Then I can pull the 1/3 outside of the integral, 3e to the 3x dx. And then I can use this derivative over here to say this is 1/3. Doing an antiderivative of 3 times e to the 3x is just e to the 3x. And I do this from x equals 0 to x equals 5. So I get 1/3. When you plug in 5, you get e to the 15. You plug in 0, you get e to the 0. E to the 0 is just 1. Anything to the 0 is 1. So you put this together and you get e to the 15 minus 1 over 3. This method here where we had a 3x here and we kind of wanted x instead of 3x, we'll do a substitution method with that later on here. Right now we can just kind of reason this through, although if you know how to do substitution, typically call it use substitution, you can do that as well. It's really essentially just getting this 1/3 out here. Next one. Integrate 0 to 2, y squared plus 3 times y minus 1 dy. Now this one, you might try and do something fancy with this product, but really what I would do is just multiply this out. So y squared times y gives me y cubed. Y squared minus 1 gives me a minus y squared. 3 times y gives me plus 3y. 3 times negative 1 gives me minus 3. So I'm going to integrate this polynomial from 0 to 2. And then I can use that rule that says the antiderivative of x to the n, dx, is x to the n plus 1 over n plus 1 plus c. We leave off the plus c's with our definite integrals. And so what we get, we can use y's in place of x, doesn't matter what the letter is. Y cubed, you do an antiderivative, is y to the 4th over 4. Y squared gives me y cubed over 3. 3y gives me plus 3 times y to the 2nd over 2. Plug in a 1 there. And then 3 times y to the 0, it gives me a y over 1, which is just y. Or often I just think the derivative of 3y would be 3. So I do my antiderivatives, and then I have to evaluate them from y equals 2, and then subtract when y equals 0. So this is all 2 to the 4th over 4 minus, let's write that a little better, minus 2 cubed over 3 plus 3 times 2 squared over 2 minus 3 times 2. So it's just this thing up here plugging in y equals 2. And then subtract when we plug in y equals 0. I'll get 0 to the 4th over 4 minus 0 cubed over 3 plus 3 times 0 squared over 2 minus 3 times 0. You'll note every term here is 0, so this whole thing goes to 0. So I want to make sure we plug in that 0. Sometimes you'll have like an e to the 0, which is a 1. I believe we had that on the previous question there. So sometimes people will put a 0 without thinking it through all the way. You want to make sure that actually is 0. You don't necessarily need to write it down, but you need to think that through. And then what I get, let's see, 2 to the 4th over 4, that's going to be 16 over 4 is 4, minus 8/3, plus I can cancel the square with the 2, that's plus 6 minus 6. So I have 4 minus 8/3, that's 12/3 minus 8/3. That works out to be 4/3. Next one. This one is probably best done as a substitution here. So we have x times e to the x squared here. What I'm going to notice here, and this is a little bit tricky, is that the derivative with respect to x, well, when we did, let's just go back to e to the 3x here. What I got was e to the 3x, but then you needed to multiply by the derivative of 3x by the chain rule. So 3 times e to the 3x. We're going to use the same sort of strategy here, where we have an e to the x squared. That derivative is like e to the x squared, but then I multiply by the derivative of x squared, which is 2x by the chain rule. So the derivative of e to the x squared is 2x e to the x squared. And then I notice that's basically like what I have here. So I'm going to rewrite this as an integral from 0 to 2, 1/2 times 2x e to the x squared dx. And then this 2x e to the x squared matches my derivative of e to the x squared. And so when I do an antiderivative, the 1/2 will pull out in front, and the antiderivative of 2x e to the x squared is just e to the x squared. And then I evaluate that at 2 minus that evaluated at 0. When I plug in 2, I'm going to get e to the 4th. Plug in 0, I get e to the 0. Note here, this is this e to the 0 equals 1. So you end up with e to the 4th minus 1 over 2. A little bit trickier. We'll get u substitution here and sort of do this more formally later on. Kind of this process of sort of guessing something that has the right derivative. Although with antiderivatives, it's a lot of times really is sort of a guessing game, or there's like an art form to it. Okay, so here's another one. Our last one of these. We're going to integrate from 0 to pi over 4 cosine x plus sine x squared. So this is typical of a lot of these trig function sort of integrals where you have to kind of do some trig manipulations before you find the antiderivative. So what I'm going to do is I'm just going to square this out. So what I'm going to get, the first thing squared is cosine squared x plus 2 times cosine x times sine x. I'm going to write it as 2 sine x cosine x, and then plus the sine x squared, that's plus sine squared x. So all I did here was sort of evaluated the square, foiled this out, perhaps you could think of it. And then I'm going to rewrite this here and use a little bit of trig identities. I'm going to do cosine squared x plus sine squared x plus 2 sine x cosine x. Now my trig identity is cosine squared x plus sine squared x. That's a Pythagorean identity. That's the integral from 0 to pi over 4. That's just 1. So this is a trig identity. Cosine squared x plus sine squared x is 1. 2 sine x cosine x is actually sine 2x. Here dx. Maybe we'll highlight this where this part gives me the 1, and the 2 sine x cosine x is sine 2x. So those are just trig identities. I didn't really do any calculus yet, really just trigonometry. Although I may be letting the trigonometry or the calculus guide me to what I want to look at or what kinds of things I want. So what I like about this is, 1, I can find an antiderivative of 1, so that's nice. Sine 2x, well, if I differentiate with respect to x, typically it's going to be the other sort of corresponding trig function, the cofunction, cosine, and I really want to have the 2x there. If you differentiated this, you would get, well, it would be a negative sine of 2x, but then by the chain rule I have to multiply by the derivative of this inside function, that 2x, I get a 2. So it's really negative 2 sine 2x is the derivative of cosine 2x. So what I'm going to do, I'm going to get 0 to pi over 4, and just keep the 1 dx, plus an integral from 0 to pi over 4. And I can have the sine 2x here. And just split my integral up. But then on the second one, I want a negative 2 here. And to sort of compensate for that, I can multiply by negative 1/2. So negative 1/2 times negative 2 is 1. I can multiply by both of those. That's not changing anything. And I just have the sine 2x. So then what I get, the antiderivative of 1 is just x. Derivative of x is 1. Evaluated from 0 to pi over 4. And then the second one, I have a negative 1/2. And then the negative 2 sine 2x, that antiderivative is cosine 2x. From 0 to pi over 4, or maybe pi over 4 to 0, depending on how you want to think of it. And so then I get plug in pi over 4 for x, gives me pi over 4 minus 0, the first one. Oops, a little stray mark there. No, I lost my vertical bar doing it. And then the second one, I have minus 1/2 times plug in pi over 4. That'll give me cosine pi over 2 minus cosine of 0. So what I end up with is my pi over 4 minus 1/2. Cosine pi over 2 is 0. Cosine of 0 is 1. So I'll get a plus 1/2, and I get pi over 4 plus 1/2. Now, one thing you should note here is this is positive. That's a good thing because the initial thing I started with is something cosine x plus sine x squared. I'm integrating something that's always positive. So this should be the area sort of between the curve and the x-axis. And because the curve is always above the x-axis, it should be a positive version of the area. So I should get a positive result. It's a nice thing to check there just to make sure you have the correct sign of an answer when you can tell. Next one. So this is going to use the other part of the fundamental theorem of calculus here. So essentially what we did so far, so this is the fundamental theorem of calculus. So there's two parts. They get switched around sometimes. What's part 1, part 2? One part says that if I do a to b of the derivative of x, derivative of f of x dx, that this is effectively f of b minus f of a. Essentially, that's what we've been doing up to this point. So one part of the fundamental theorem of calculus says if I have an integral of a derivative, something happens where it's effectively that function. The second part says that if I do a derivative of an integral, now what I'm going to get is a to t, maybe f of t dt. So essentially the derivative of an integral, that's just going to be f of x here. So essentially what the two parts of the fundamental theorem say is that I can, in some sense, view integrals and derivatives as inverses of each other. So an integral of a derivative is essentially this function, but we have sort of this subtract f of a here. I do a difference at the endpoints. Also, a derivative of the integral is sort of the initial function, but I have to add this starting point of a. So it's not quite that they're exactly inverses, but essentially that's sort of the idea. Okay, so now as an example here, you can just use this real quick on y equals integral 3 to x, t, e to the t dt, find dy dx. Well, y is this thing here. A is 3. Really, okay, oh, sorry, I messed this up in my statement. That t really should be an x. Derivative with respect to x, a to x. T is the thing that I'm integrating. So that was all wrong before. That should be a to x. It's probably confusing. So this, what I'm integrating here, and I have a t times e to the t. That's my f of t, dt, and I have 3 to x. So the derivative dy dx, all that the fundamental theorem of calculus, second part, the way I've got it written here, is saying that my derivative is just x e to the x. Essentially, that's all that's there. Now, I think this part, in some sense, is much easier to deal with, but it's somehow more confusing as well. So let's look at a picture of this. So here, I've got a graph of that function. It was t times e to the t, or really yeah, t times e to t, and I'm going from 3 to x here. So this function, so if we go back here, y is really the shaded area under this curve, and I've got this slider up here where I can move x around. So there's x equals 3, so that's no area, and I can sort of get more and more y here. So really this is saying that the x value is out here, and then the function value is the area of the shaded part. And that sort of changes as I increase x here. Now, what this fundamental theorem is saying here, what this derivative is saying, is that the change of y, so how fast y is growing, is really just x e to the x here. So there's a couple points of this. First of all, it shouldn't rely on 3, whether this started at 1 or 2 or 7 or -8, as long as my functions sort of behave well enough on the interval I'm dealing with. Doesn't matter where I start, and that kind of makes sense here, because we're talking about how fast this region is growing here. So if I at 4.5 or so, and I grow, how fast I'm growing doesn't really matter if I started at 3 or 3.5 or 1. I really only care about what's happening near 4.5. So that left endpoint really shouldn't matter at all. So the hope is that intuitively makes sense that this a really doesn't come into play on the right-hand side. The other thing is, why should this derivative be f of x? Well, if you think about how fast is this function growing, if I just increase my x by a little bit, essentially I'm going to add a rectangle here whose, well, width is going to be like a delta x, but its height is essentially f of x. And sort of the rate of change should be, well, whatever the height is right now. So sort of that's going to change quickly as I move x. But it should give you some sense that how fast this shaded region grows is really the same thing as the height of the function. Okay, so that's the general idea. Hopefully give you some sort of intuition with the picture. Now, you can make these questions more complicated. Sometimes this is the kind of thing that really shows up. We have y as 3, integral not from 3 to x, but from 3 to square root of x. And that's cosine of theta to the 4th d theta. So what we have to do is I'm going to let y be, how about f of g of x, where, let's say, f of x is really the integral from 3 to x cosine theta over to the 4th d theta. And then g of x, I want to do f of g of x to be y. G of x is then square root of x. So if I put in a square root of x where the x is, I get y here. So I can write y as a composition, and that means by the chain rule, dy dx should be f prime of g of x multiplied by g prime of x. So this is our chain rule here for derivatives. Well, what's f prime of x? Well, that should just be cosine of x to the 4th. So what we're going to get here, maybe I'll write these in green, how about red to set them off? F prime of x, by the fundamental theorem of calculus, is just cosine of x to the 4th. G prime of x, so remember g of x is x to the 1/2. Square root of x is another way to write that. So g prime of x is 1/2 x to the negative 1/2. So what I get is f prime is cosine x to the 4th, but it's f prime of g of x. So that's cosine of square root x to the 4th. But then I have to multiply by g prime of x is 1/2 x to the negative 1/2. Now, square root x is x to the 1/2, so square root x to the 4th is actually just cosine of x squared. So I get cosine x squared, and then x to the negative 1/2 I can write as 2 over square root of x. So I can put the 2 in the denominator, negative exponent puts an x to the 1/2 in the denominator, that's a square root of x. So there's really our derivative. Essentially, we're using the fundamental theorem of calculus, but with the chain rule thrown in. Next one. Similar idea, but there's another twist here. My bounds don't match up. So my fundamental theorem of calculus says I have to start at a constant and go to x. We don't have an x there, but the constant's the top one. So the first thing I'm going to do is say this is negative the integral of switch the order of the bounds. 3 to x squared e to the t squared dt. So that's y. And so dy dx is a negative of derivative of this function, essentially is e to the t squared, well, e to the x squared if I had an x there, so it's going to be x squared squared, but then I have to multiply by the derivative of this inside function, which is x squared, that's 2x. So I end up with a negative 2x e to the x to the fourth. Let's just box that up there. Next one, I want to do some more integral manipulations. So this one, I can rewrite this integral here as an antiderivative, or so let's say an integral. Let's do, how about natural log x to a, let's pick a number, how about 2, that makes sense with natural log x, 1 over t dt, plus an integral from 2 to x, 1 over t dt. And then I'm going to do another manipulation. I need this 2 in the bottom, so I get a negative integral from 2 to natural log x, 1 over t dt, plus an integral from 2 to x, 1 over t dt. So I'm just using properties of integrals to rewrite y here. Well, now the fundamental theorem says dy dx. This first one should be, well, a negative. I should get a 1 over the thing function up here, natural log of x, but then I have to multiply by the derivative of natural log x by chain rule. Derivative of natural log x is 1 over x. This one, when I differentiate integral 2 to x, 1 over t dt, should just give me 1 over x. So what I end up with is maybe 1 over x minus 1 over x, natural log of x. Here, and maybe you could rewrite that in some other way using that common factor of the denominators of x, but not seeing anything that's going to happen that's super nice. Okay, another type of question here. I want to find the area between the graph of y equals f of x and the x-axis. So first of all, let's see sort of the wrong way to do this here. Is a lot of times what people will do is they'll just integrate this 0 to 4, x squared minus 5x plus 6, go dx. So this is sort of the height of my function. I go sort of integrate from 0 to 4. Again, this is the wrong way to do this. Integrate x squared gives you x cubed over 3. Integrate x gives you an x squared over 2. You get the 5 times. Plus 6x, go from 0 to 4. And I evaluate this, plug in the 4. I get 64 over 3. 4 cubed is 64. 4 squared is 16. Divided by 2 is 5 times 8. 6 times 4 is 24. So I get a minus 40. Let's see, minus 40 plus 24, it's a minus 16. So that's 64 thirds minus 16. That's 64 thirds minus 48 thirds. That gives me a 16 thirds. So that looks sort of reasonable here, but there's a problem here. Now, I'm not actually asking for the value of this integral. I'm finding the area between the graph and the x-axis. So there's a very slight difference here, that what I'm asking for is really the integral of the absolute value of x squared minus 5x plus 6 dx. So if x squared minus 5x plus 6 is always positive, this should give me 16 thirds. But it's not. Here, let's look at our graph. So here's the graph. You'll see my x squared minus 5x plus 6 dips below the x-axis here. So what we can do, there's a couple ways to approach this. Essentially, you saw, well, we can figure out where x squared minus 5x plus 6 is 0. So let's maybe do that up here. X squared minus 5x plus 6 equals 0. Well, this factors as x minus 2 times x minus 3 equals 0. So that's at x equals 2 and 3. And so that tells you I'm going to be negative between 2 and 3. So I could sort of draw my number line here. I have 2, 3. This function is positive for anything less than negative x. It's negative between 2 and 3, positive for really big things. So x squared is going to dominate here for both, well, really, really negative things like toward negative infinity and really, really positive like towards positive infinity. Those will both be positive. It'll be negative in the middle. You could plug in a value of 2.5 and figure that out. Or, you know, this is a parabola, and if it's 0 at those two places and it goes up, it has to be negative in between. So what that means in terms of the integral is essentially this integral. I go from 0 up to 2 of x squared minus 5x plus 6 dx. And then from 2 to 3, I don't evaluate this, I evaluate negative of that. So I'm going to really do plus the integral from 2 to 3, negative of x squared minus 5x plus 6 dx. And then from 3 to 4, I go back to the original function. And my dx off to the side there looks really ugly. Okay, now another way people do is move this negative out here and say I'm going to subtract the function value there. If you look at your graph, the integral actually be negative here, so I'm subtracting the negative area. Or you just integrate from 2 to 3 and take the absolute value and add that. There's multiple ways to think about this. In any case, this first integral, well, they're all going to be x cubed over 3 minus 5x squared over 2 when I find my antiderivatives, plus 6x, and that goes from 0 to 2. I'm going to pull the negative out, get the same x cubed over 3 minus 5x squared over 2 plus 6x. That goes from 2 to 3. And then plus integral x cubed over 3 minus 5x squared over 2 plus 6x from 3 to 4. So you just plug these in. Plugging in 2 gives me 8/3. 2 cubed is 8. 2 squared is 4 times 5 is 20. Minus 20 over 2, that would be 10. Plus 12. When I plug in 0, everything is going to be 0, so I don't need to worry about that. Minus, plug in the 3, 27 over 3, that's 9. 3 squared is 9 times 5, that's minus 45 halves. Plus 6 times 3, that's 18. When you plug in the 2, you're actually going to get this exact same thing over again. So you'll get an 8/3, so it's going to be minus that, but the negative out here will make it positive. You'll get 8/3 minus 20 halves plus 12. So I can just do a 2 times that. And I really doubled up that 2. And now this last one, I'm going to get plus, whoops, not 4, but 4 cubed. That's 64/3. 4 squared is 16 minus 80 halves. 5 times 16 is 80. Plus 24. And then I'm going to subtract when I plug in 3, but that's this whole thing here. So really I get 2 of those as well. And now I'm just going to go to my calculator. Be a little bit lazy about this, perhaps. And I'm just going to ask my calculator to do this for me. 2 times 8 divided by 3 minus 20 over 2 is 10 plus 12. Probably could have done 12 minus 10 in my head. Minus 2 times, see, 27 over 3 is 9 minus 45 divided by 2 plus 18. And then plus 64 divided by 3 minus 80 over 2 is 40 plus 24. And that'll spit out some kind of answer. It's 5 2/3. Convert that to a fraction. When I get done, my area is 17/3. Note that's bigger than the 16/3. Essentially, that means that, so the difference is 1/3. So half of that would be 1/6. So the area from 2 to 3 really should be 1/6 here. And the difference here is up here we're subtracting the 1/6. Here we're actually adding the 1/6. So that add or subtract 1/6 gives us a difference of 2 times 1/6 or 1/3. Next one. Same idea here. I'm going to find the area between the function f of x equals cosine x and the x-axis. So here, I'm again going to worry about where is cosine x equal to 0. Well, that's going to be x is, well, there's an infinite number of points, but I really only care about the ones from 0 to 5 pi over 4. Think about this, that's only at x equals pi over 2. So my graph is this graph here. I'm going to go from 0 to, this is like 1.5. This is going to be pi over 2 there. So I go 0 to pi over 2, I'm positive. And then from pi over 2 to 5 pi over 4 is here. This is negative. And it would switch over to 0 again, but that's not in our integral. And so what we get is our area. It's going to be an integral from 0 to pi over, well, let's write that more nicely. Integral from 0 to pi over 2 of cosine x dx. And then I'm going to subtract the integral from pi over 2 to 5 pi over 4 cosine x dx. So effectively what I'm doing, let me just write equals here, I'm doing an integral from 0 to 5 pi over 4 of the absolute value of cosine x dx. So I'm doing that absolute value, and this splitting from 0 to pi over 2 and pi over 2 to 5 pi over 4, just dealing with the absolute value. So from 0 to pi over 2, cosine x is positive. You can just drop the absolute values. From pi over 2 to 5 pi over 4, cosine x is negative, so I have to do negative of the negative, gives me the positive version. Okay, now I have to think, what differentiates to cosine x? Well, my instinct is, well, it's going to be right. It's going to be sine x. So I always have to worry about, is this positive sine x or negative sine x? Derivative of sine x is cosine x. This is the one I want. 0 to pi over 2 minus sine x from pi over 2 to 5 pi over 4. Incidentally, if I'd done sort of negative sine x instead of positive sine x, if I was consistent with that, I should end up with a negative answer, which I can tell right away should not be an area here. So sort of self-correcting if I'm willing to sort of believe what I wrote down. So now I just need to evaluate this. Here, plugging in pi over 2 for x in the first one gives me sine pi over 2. This plugging in is 0 gives me a minus sine of 0. That's my first grouping. Second grouping, I plug in sine 5 pi over 4, and then I subtract, plug in pi over 2 for x, sine pi over 2 here. And so what I get, when you look at this, I get sine of pi over 2, that's really 1, let's maybe work this out, 1, sine of 0 is 0, minus sine of 5 pi over 4, so let's see, on my unit circle, 5 pi over 4 is going to be here, so it's going to be a negative square root 2 over 2. Sine of pi over 2, that's a minus 1. And let's say I get the negative there, so this is going to be 1 plus square root 2 over 2 plus 1. So in the end, I end up with 2 plus square root 2 over 2. And that's a positive answer, and this should be an area, so that at least seems plausible.